Hi, folks. I'm Bill Lionheart from the University of Manchester, and this is the first of hopefully a series of little tutorials on numerical methods for inverse problems. We'll start in one dimension because those inverse problems are quick and easy to visualize, and the hope is to continue to tomographic inverse problems in 2 and 3 dimensions. Let me share the screen. Okay, so I have opened a MATLAB notebook here, which I will put a link to in the notes below. I'm going to use Per Christian Hansen's regularization tools, which you can see here on this link, and download it from the GitHub site. The manual in there, the PDF, is actually quite a nice tutorial book on inverse problems. So that would be well worth study in itself. I'm only going to use a few of the examples from this toolbox. This is a MATLAB live view kind of notebook format. If you read it as an M file, you can convert it to MATLAB Live. If you've got a PDF, I guess you can still just copy the code into your MATLAB command line. You now need to download regularization tools and add it to your path somewhere. So replace this by wherever you've put it. I'm on a Linux system, so the slashes are forward slashes. Okay, so our first very simple example is deriv 2. Essentially, this is the inverse problem where the forward problem is differentiate twice. That means it's an indefinite integral twice, right? But you know, it depends slightly what the boundary conditions are. Anyway, the point is differentiating twice numerically is unstable because if there are sharp changes in the function and then you take differences in nearby values, obviously that's very sensitive to noise. Okay, so we set the size of the problem to be n, and I'm going to call deriv 2, which generates a matrix A, a vector B, and a vector X. And the idea is A times X equals B, but you want to try and find X, knowing only A and B. A is 100 by 100 matrix. Let me just click to run section is Control Enter. Okay, so the output comes out over here. It's 100 by 100 matrix. If we look at A times X minus B and then take the norm of that, we see it's something like 210 to the minus 6. So AX is very close to B, and the plot of X and B looks like this. So this is the function we're looking for, and integrate it twice, you get something smoother. So that's the B. It's plotted as a function because it's a vector. You have to know what X values were used on the axis for, well, X as a function. In the documentation, it explains how it converts the function into a matrix using quadrature. Okay, it's got a parameter example, and that just makes it different, right-hand side, B, and of course, X. Well, how well conditioned is this? If we look at the condition number, the simplest just cond of A, it tells us that, I should do Control Enter to make sure it's just run. It's about 1/10 to the 4, so it's reasonably hard to solve, but not terribly. And later on, when you try yourself, you can see what happens when we make n bigger and see whether the condition number gets worse than what we expect. Okay, so let's just try solving it using backslash and see what happens, which is kind of maybe the first thing to try. So here, let's call it x0 is what we get by doing a backslash b with nothing fancy. And it turns out, because the condition numbers only 10 to the 4, it gets a pretty good solution, right? So the error in the solution, the norm of the error is 10 to the minus 18, so to floating point precision, essentially. And if we take the difference between the x and x0, we see, apart from a little bit near the middle, and I'll wipe this out, that's errors in the scale 10 to the minus 5. So that works fine. There's no difficulty with it. We did the inverse crime, as we say, of using the same matrix A as was used to make the data B, and also doing it at the same level of discretization, using the same numerical approximation. A simple way to make it a little bit more realistic is to add some Gaussian pseudo-random noise, which is easy in MATLAB, and then we'll see how well that works. Okay, so how do you do it? I use this expression. So rand n makes a normally distributed variance 1, mean 0, pseudo-random vector of size, the same size as B, so 100 by 1 in this case. I've set I'm thinking of it standard deviation to 0.1% here. But to scale it correctly, I've multiplied by the norm of B. So it's as a proportion of the overall size of B, so it scales well. So looking at the plot of B here, you see that I've very slightly changed the data. But what happens when you differentiate it twice? Well, if we just do backslash the standard least squares solution in MATLAB, which attempts to solve it directly, we get basically just rubbish. And the difference between the actual and real solution is also all over the place. So that didn't work. And even though with a fairly small 0.1% level of noise. Okay, so when we have an ill-conditioned matrix like this, and an ill-posed or unstable inverse problem, the first reaction usually is to try Tikhonov regularization. And very simply, that means instead of trying very hard to fit the data, we don't allow the solution to grow too much. So we constrain the solution so we don't get huge values in that vector, and trade that off against fitting the data. The formula for Tikhonov regularization with the identity matrix, the simplest type of Tikhonov regularization, it is A transpose A plus the Tikhonov factor squared times the identity matrix. Well, actually inverse times A transpose times B. Of course, this matrix for a non-zero Tikhonov factor is square and well conditioned. So this is just the same as inverting the matrix. Okay, so Control Enter on that one. Let's just see. Okay, so now the Tikhonov regularized solution with that Tikhonov factor, I just chose 5e to the minus 3, and you see it's pointy, but it rounds off the top. Okay? So it slightly smooths the solution, and assuming the solution is a bit smooth allows us to stably solve for it, which is a bit like saying, well, if you knew the solution was meant to be smooth and you were doing numerical differentiation, obviously that helps. I chose the Tikhonov factor just by trial and error, and I encourage you to try different Tikhonov factors. There are suggestions for things to do here, and my idea is that you can just change this code a little bit. You change the Tikhonov factor, you can change n, and so on. Change the level of noise, see what happens. Okay, so that's a very quick bit of regularization. The singular value decomposition, in particular singular values, is a method to tell how ill-conditioned the system is. Essentially, it gets the matrix and gives you an orthogonal basis for the space where the x lives, the unknown, and an orthogonal basis for the space of data. In that basis, the matrix is diagonal. Those diagonal and non-negative elements in order called singular values. And they're saying that the vectors in the unknown side are listed in order of how hard they are to find, right? Because the component that vector gets scaled by the singular value, and the smaller the singular value is, the less effect it has in the data B, so the harder it is to invert. So the first few are easy, and then they get harder. The faster the singular values decay, the harder the problem is to do. And of course, it also depends how many data points you have, because underlying this, we have the idea that these are operator equations for functions, and we've just taken some numerical quadrature to turn them into matrices and vectors. Okay, so in MATLAB, the singular value decomposition is very simple. USV equals SVD of A. There are options, but this is the simplest way. U and V are matrices whose column vectors are the singular vectors, and S is a diagonal matrix of the singular values. It says it's 100 by 100 there, of course. Now, to plot the singular values, I've just done diag. Diag of a matrix gives you diagonal. Diag of a vector gives you a diagonal matrix. So semi-log y is a log linear plot, and deriv 2 here on a log linear plot, you see you see the singular values going down, and you wonder actually if that's a power. And so if we plot on a log-log scale, so log-log diag of S, we see it's pretty much a straight line, meaning that it has a power law, so we can do the slope and intercept of that graph to get the power law. Let's try and do this. Okay, so you can do the slope and intercept, the linear regression how you like, but actually it's easy to do it with backslash. So I make a vector of the n's, 1 to n, and a vector of the logs of the n's, right? We also make a vector of the logs of the singular values. I had to reshape, of course, some of these end up as row vectors. So our regression vector, which is the slope and intercept, the intercept and slope, I get from solving this system. So I've got a row of ones, and then I've got a row of logs of the n's, and then on this side I've got the logs of the singular values. And the idea is the intercept multiplies the ones and the slope multiplies the values and gives you this. So the slope is the second component of my vector regress, and the slope is minus 2 and a bit. And there's some intercept, which is just a matter of scaling, I guess. Okay, so roughly goes like the power of minus 2, because it doesn't fit exactly, the little turn up at the end. It gets harder to calculate singular values as they get smaller because of round-off errors. Anyway, it roughly goes like a power of minus 2, which is consistent really with the idea that a integrates twice. I mean, we'll look at that a little bit more later. If you haven't seen linear regression done this way, just maybe just write it down in pencil and paper and see if you agree that solving a least square system is the same as linear regression. Let's look at the singular vectors. We haven't seen those yet. So U is the left singular vectors. Just remember, forget which is U and V. It's AV equals US is the decomposition. But actually the left and right singular vectors are pretty much the same. And if we plot them, so I've plotted the first 5 here, all the whole columns number 1 to 5. And so in order, it gives us, well, just looks like a Fourier basis, some sine waves with different frequencies, right? Well, notice actually, well, it comes to 0 at the end. These are the right-hand side, and it shows that we can really only get, that this basis only spans functions at 0 at either end, right? Anyway, so roughly, of course, we can do differentiation in frequency space by multiply by I times frequency twice, up to some scale factor, depending on your definition of Fourier transform. And then integrating would be dividing by frequency squared. The frequencies are integers, so 1 over n squared, and that's the -2 that we see. So in a way, we didn't need the SVD. We could have just done it in terms of Fourier series. Anyway, the same holds roughly that negative powers are operators that are roughly integral operators, and their inverse is a differential operator, which will be unstable, but not so very unstable. A bit of smoothing should fix it. We call those mildly ill-posed. Well, in regals, there's quite a few examples, and some of them are severely ill-posed. One is the backward heat equation called heat, and the other, the truncated, I guess, inverse Laplace transform. So let's look at the SVD of those. So here we've got AXB is I Laplace n example, I guess examples 3. Doesn't matter. USV equals SVD of A. It's got the singular values. And we've got semi-log y of S. And on a log linear scale, actually what we see is the first singular value is huge. And then what happens to the rest? So if you plot from 2 to 10 on a log linear scale, actually that's a log scale, isn't it? No, it's a log linear scale. Okay, so for they are decaying fairly kind of reasonably like that on a log linear scale, at least over that part, but they drop rather dramatically if you look a long way. In fact, going down to 10 to the minus bigger than 15 really just counts as 0. I mean, so it will calculate singular values like that, but they're really lost in rounding error, and we treat them as 0, whereas we usually think that at least this part means something. In other words, if we took more and more accurate approximations, it would tend to some sensible limit. Okay, the backward heat equation isn't quite so strange. Actually, there is a whole literature on truncated Laplace transforms, and in some cases, their spectrum of the operator is not discrete, so it's not so straightforward to see what the singular values calculated numerically would do. Backward heat is a bit easier. I mean, of course, you can solve the heat equation using Fourier series as well, it's fairly easy to understand how that works. The point is that the forward heat equation, you get a distribution of temperature, and as time goes on, it smooths out the distribution of temperature. And the backward heat equation, and so typical of inverse problems, it's not a problem that's solved by nature. You have to take this smooth temperature distribution and say what was the temperature distribution an hour ago. And so, of course, it depends how quickly the heat diffuses. And so we've got parameter kappa, and certainly for kappa equals 1, it's severely opposed. I think maybe when kappa gets to 5 in this one, it's fairly well conditioned. So here, let's plot the singular values on a log linear scale, and we see that they are decaying. So on a log linear scale, they're going roughly, so not exactly a straight line actually, but bottoming out to a straight line for this bit at least before something else happens. And so faster than any power, and so something like an exponential. Okay, so these approximately 0. The correct solution for this example is this curve. In other words, that's the temperature distribution at time 0 that we're looking for. And in this case, it's fallen off. Yeah, right. So I've tried kappa equals 2 here. It's not shown on the display. And what you see is the singular values. It's only really the last singular value that shoots down, suggesting really that the null space is actually one-dimensional as you take a sufficiently accurate approximation. Okay, so that singular value is the last of the V's. The V's are the ones on the X side of things. And if you look carefully, it's just a spike at the end. And it just means that we've made the problem so that we can't find value number 100. And if you look carefully at the way the problem's set up, that's understandable. But, don't worry about it for the moment. As a quick hack, though, let's just eliminate that value number 100, the end one, because we know we can't find it anyway. So here in MATLAB index notation, I've just chopped off the 100th value, the last one, of A and X, and then made new data, the reduced data, AR times XR. And then if we use a Tikhonov factor, again, you can just play with it to see what's suitable. And here's the formula for Tikhonov solution using the backslash operator, and with the matrix with the last row, last column chopped off the matrix A, we see we get something that's fairly close, starting to be a little bit wrong at the end. Okay, so I encourage you to try different Tikhonov factors and also maybe think a little bit about this hack. Obviously, if you see one singular vector with singular value 0, it's worth looking at that at both the V's and the U's to see what's going on, because that's a component that you can't find in the solution and a component you won't get in the data, right? So perhaps rethink the problem suitably. Oh, this hasn't rendered correctly in LaTeX. Hopefully you can read LaTeX. So Tikhonov regularization can be formulated as minimize over x, ax minus b norm squared plus, well, that's probably it, alpha squared, where alpha is the Tikhonov factor, Lx, where L's some matrix squared. We took L to be the identity so far, but in general, it could be a sparse matrix that approximates a numerical derivative. or a combination of that with the identity, perhaps. When it says live MATLAB, it means I can live correct my spelling mistakes. So because this is a quadratic minimization problem, it means that the derivative of a quadratic is linear, which means we can solve it with linear algebra. That's kind of why Tikhonov is easy, and we've got a linear algebra solution to it like that. But there's a neat little trick to avoid working out A transpose A, because if A is really big, that might be a problem. And for example, also A might be quite a sparse matrix, but A transpose A might be much denser, for example, and so require more storage. In any case, we'd like to save that trouble. And a way to do it is to, and we're going back to the deriv 2 example. I've just redone the deriv 2 example. I make the augmented matrix A, which is a 200 rows by 100 columns matrix, whose top block is A and whose bottom block is alpha times the identity matrix, or in general, the L matrix you're using for regularization. It's 200 by 100 matrix. And then the B vector, I've just stuck a bunch of zeros in. And you just think, I've just made a big overdetermined system of equations. And the first bunch of equations says Ax equals B. And the second bunch of equations says alpha X equals 0. And so the point is, it's overdetermined. So you can't actually solve those all consistently. But if you do the least squares solution, it trades off between making X small, alpha controlling how small, and fitting the data Ax equals B. So that can just be solved using backslash, and that should be more efficient, and certainly you can implement it in a more efficient way, and it gives you the same answer as before. More generally, you only really need A times a vector and A transpose times a vector to solve a linear system of equations. And iterative solvers especially tend to be combinations of A times vector and A transpose times vector, and maybe some norms. So when the matrix is a bit too big to hold in memory, even with sparse storage, calculating it on the fly, in other words, just calculating a row or a column of A as you need it, turns out to be a way to fit it in memory. So there's advantage of iterative algorithms, and we'll come on to them in a moment. Have a look at some other examples in regtools. Just look at the SVD and see if you can understand if we'd say they're severely or mildly ill-posed. And also have a go with just increasing the n, the number of points in our discretization, because if the underlying operator problem, if our numerical approximation converges to the underlying operator problem, we'd expect that as we increase n, the singular values will come in some pattern, which is the same formula as the limiting case. I mean, it's not true of all operators, especially perhaps those without discrete spectrum. But for a lot of the problems that we have that are based on a compact operator on the Hilbert space, that will work. And typically, of course, as the matrix gets bigger, you'll go further down this list of singular values for the infinite dimensional case. And so the condition number, which is the first singular value divided by the last singular value, will increase. So the more accuracy you need in the solution, you're tempted to collect more data, but there's a kind of diminishing return given by the singular values. So this augmented matrix has a perfectly reasonable condition number because we added deliberately added that taken off regularizing block. So in this case, it's 20, and that means that well, a lot of iterative solution routines will converge more quickly the smaller condition number is, and so we can apply iterative methods to the augmented matrix. One of the nicest ones we have is CGLS, and I'm using the implementation in reg tools, partly at least because it tells us all the iterations as you go. It's only a few lines of code to implement CGLS, so you can customize it to fit the kind of matrices that you want and make it more efficient. So what CGLS spits out, and I've given it 10 iterations, usually you would see what happens after 10 iterations and see if you need more, or you'd have a stopping criteria based on the number of iterations. But just for looking at it, it's pretty good. The X that it spits out is for each iteration, it gives you a column which is a solution X. So we can see all the solutions. And it solved it to 0.00 roughly 14. So of course it can't solve it exactly. We can't get the error down to 0 because it's a system of 200 equations and 100 unknowns. So, and it is inconsistent. So we're not going to get an exact solution, and it will get the solution with the smallest norm, which is taken off regularized solution in this case. The row and eta it spits out are the lists of the residuals. So the norm of ax minus b for the current iteration x, and the norm of the solution, which if it's converging to a solution, the norm should also converge. I mean, of course, the norm converging doesn't mean the x is converged. It could be sort of going around in a giant n-dimensional sphere. Okay, anyway, we see that the residual drops dramatically on the first iteration. Right? So actually that's iteration 1 and that's iteration 2. So it's probably best just to check that the norm of BA where have I got it? Let me just do. Yeah, the norm of BA is 0.02. Why do we care about that? Well, if you put x equals 0, right, which is the default starting value, then ax minus b is just the norm of b. Right? So so the 0th iteration you like is 0.02, and the first iteration of conjugate gradient least squares already takes it down to 0.001 something. And then I think I just zoomed that window there. But then in the next iteration takes it down again. And after that, it doesn't look like it's changing very much, at least on this scale. So these are the etas. And again, we see a big change in the norm of the solution, or relatively big change. You know, look at the scale, it's not that big a change. But then it settles down, presumably because the solution's converging. Well, we can plot each iteration. Here's my plot of each iteration. So here's 1, 2, 3, 4, 5, and 10. There's a kind of diminishing return as it gets towards 10, but it does get more and more pointy. So while it's making a very subtle change, and you know the difference between this and the actual solution, which is a point there, of course, it's only kind of one value in 100. So it's not making a huge difference to anything, but you need those to use the components with the very small singular values to get it. Okay, so remember though that we're still doing an inverse crime. So we haven't added any noise to our vector B. So it's not surprising because it's mildly opposed that we can solve it. So what happens if we just did CGLS on the matrix A with the inverse crime, and see what the iterations look like for that. Well, it turns out that the effect of successive iterations is very much similar. In fact, you always think you can either change the Tikhonov factor or the number of iterations you do CGLS, and both of them smooth the solution. So now let's add some noise and see how much we can mess it up. You can play with different noise levels. Here I added 1% noise, which is a lot. I mean, that really messes up that right-hand side vector B, so you think we're lucky to get anything. So here is CGLS iterations with no regularization. And here I've just plotted x1 to 4. And so you can see what happens is it's got off to a good start, but once you've gone beyond fitting it to a certain level, it's just fitting the noise, and it's explaining it by kind of wild high frequency components in the solution. So CGLS, but just on matrix A, not the augmented matrix, it's working. Because CGLS is very quickly converging, so you notice in 2 iterations it's got pretty much there. The point at which it starts including the noise, because it's already more or less fitted it, the solution, is quite early on. So so CGLS does work as a regularizer, but it goes very quickly. So you don't have much choice between iteration 1, 2, and 3 as regularized solutions, because iteration 4 is rubbish. So as far as a regularizing iterative solver, it's not so useful. And also the regularization it imposed, well, it looks kind of reasonably the same in this problem, which of course is really just a filter in the Fourier domain. The general problem is that using iterative methods to solve as a regularization method without adding that augmented block means you kind of don't know what the regularization is that you've imposed, rather than knowing something a priori about the solution. And also what it does impose depends on the matrix A, which is often not physical. I mean, the X was sitting there minding its own business, maybe you knew something about it, and then you take measurements A, and X didn't know it was going to be measured with A. So the sort of likely values that it might take really shouldn't depend on A. Okay, so for more things on iterative regularization, IR tools is a good link. It's there. I'll put it in the notes. So you can play with a lot of iterative tools and regularizations. There's some tutorials using iterative methods for tomography problems, so 2D problems. I recommend this tutorial, which uses air tools, another one of Per Christian Hansen and his collaborators' toolboxes in MATLAB. And so feel free to play with that. This was just a taster. I will make some more videos in this series, I hope. I'm happy to accept requests, may or may not do them, but my plan is to work my way through to 2- and 3-dimensional problems, and also cover Tikhonov and sparsity promoting regularization schemes, as well as smooth ones. Thanks very much. Stop the share there and see you next time.